Hello, everybody. My name is Bruno Bertrand, and I'm working at the Royal Observatory of Belgium. And today I will present my talk about probing primordial black holes and dark matter clump in the solar system with global navigation satellite system. So as you know, there are strong evidence of gravitational anomalies at the large scale of the universe. And the main hypothesis is a dark matter. But at the other side of the scale, no fundamental dark particle was found after 40 years of research. And so the idea is to see at another scale, considering that dark matter in the galactic halo could fragment into macroscopic structure called dark matter clumps, forming massive compact objects or a primordial black holes. And so it offers a new scale to track dark matter and so new ways of detection. And here we propose to use global navigation satellite systems. Of course, the newest is the American GPS, but you have also the Russian one, the Chinese one, and the European one called Galileo. And what is very interesting that with GNSS system, we have atomic clocks in orbit providing precise timing signals. We have also, for free, at our disposal, 29 years of free archived and already processed data, clock data with bias on clock synchronization, and also precise orbit product, where for each satellite we reach daily accuracy below 25 millimeter this last decade. And so the idea is to use the GNSS constellation as a gigantic detector of new physics like dark matter, where we can have two ways of detection. First, using the gravitational interaction and its impact on GNSS orbit. Second, to study the coupling to ordinary matter of exotic physics and see the impact of GNSS clock. And in the first part, we will consider GNSS orbits by observing asteroid mass, dark matter clumps, and primordial black holes in the solar system using the GNSS networks. Primordial black holes were formed in the early universe, and for the mass range of interest, the size is equivalent to less than an atom with no accretion disk. So it is a very good candidate for dark matter behaving like a heavy particle. And at the same time, we will consider also dark matter clumps of asteroid mass. The mass range for PBH is well excluded above 10 to the 21 kilo, thanks to a micro lensing at the galactic level. But below, there is a problem. There is no exclusion. Of course, there are some investigation like solar system ephemeris, but between 10 to 6 and 10 to 16, there is no way to exclude primordial black hole of asteroid mass. And the question is how to fill in the gap. And what we propose is to use GNSS systems by study the nearby encounter with the Earth and how this encounter should affect GNSS satellite orbit. The question is that, okay, but what would be the distance to the Earth, the mass of the object, and the frequency of a nearby encounter with the Earth? And for that purpose, we have studied orbital characteristic of primordial black hole of asteroid mass in the solar system. Using a Monte Carlo synthetic population, we have modeled a very large number of orbits characterized by an excess velocity, an impact parameter, and other Keplerian angles. And with a given density of dark matter in the solar system, we have obtained as an output the flux of dark matter clump mass, the distance of Earth's closest approach, and the velocity. And all these three elements are put together in this graph where the color map is related to the flux of mass. Then the question is that what is the effect on GNSS satellite? So we have modeled the effect of a third body perturbation on GNSS satellite orbit. It can be described by an acceleration profile compared to the unperturbed gravity field. And the effect has two contributions. First, the direct effect on the spacecraft, and second, the Earth record. And we obtain as an observable the time variation of the semi-major axis compared to the reference orbit. With orbit known with a precision of 3 centimeters every 5 minutes, we obtain a sensitivity to variation of semi-major axis induced by the dark matter event below 1 millimeter. And this is the result of our modeling of change in semi-major axis for the whole Galileo constellation. We can see that a very characteristic pattern, which is a step-like pattern, different for each Galileo satellite when we simulate the encounter of the Earth with a dark matter clump or PBH. So this leads us to a preliminary sensitivity analysis. We make a one probe sensitivity where we consider individual Galileo satellite spectral density and from which we derived the standard deviation of the semi-major axis. It is represented here in pink for one satellite. And to this graph, we added our simulated event of a given duration delta t using our modeled PBH orbit with different value of the impact parameter and velocity. And we can see a sensitivity area where it could be detectable by one probe. It corresponds to a minimum mass of 10 to 15 kilos at a distance of 20,000 kilometers. Conclusion, first, we obtain a very characteristic state-like signal which provide a clear pattern for future data analysis because the obtained signal does not mimic any known systematic effect. Very important. Second, if now we extrapolate our result of one probe to the full Galileo constellation, we obtain a potential sensitivity of a total dark matter clump or PBH mass of 8 times 10 to 18 kilo within a sphere of 3 astronomical unit radius. If you want an analogy, it represents 1 over 400 of the mass of the main asteroid belt orbiting within this 3 AU radius. Conclusion, the GNSS is currently the best possible test for the density of dark matter clump and PBH in the solar system. In the second part of this talk, I present study of transient variation of fundamental constants using the Galileo constellation. So here we study the coupling to ordinary matter of exotic field and the impact on GNSS clock. It is a more phenomenological approach, which is model dependent, but it offers a very interesting test of local position invariance. So the phenomenological model, we start from a quadratic coupling of a light scalar field to standard model field, where we have the coupling to electromagnetic field, the coupling to fermion fields, and and eventually a self-interesting interacting potential. And it is a very well-known fact that this kind of Lagrangian density leads to an apparent space-time variation of fundamental constant, the fermion mass, and the fine structure constant. And the idea of this project is to use data from atomic clock on board Galileo satellites to test transient variation of fundamental constant lasting from 1 day to 1 year. And for that purpose, we use a profile of a toy model domainal solution to describe the transient variation of the scalar field. Of course, the variation of phi implies an energy cost upper limited by the local dark matter energy density. And the idea is to how to describe such transient variation of fundamental constant, but you use a model of transient dark matter clump resulting from the condensation of the light scalar field and crossing the Earth. We also choose to consider large objects, so objects of which the size far exceed the Galileo constellation scale. It enables to approximate the transient variation of fundamental constant with a planar symmetry. And so a shift in energy level inside the transient dark matter clump will lead to transient shift in RH maser clock frequencies on board Galileo satellite. So there will be a clock bias between the two clocks A and B induced by the presence of the object. And from the clock bias, we can calculate the frequency bias between the two clocks considering a time sample of 30 seconds. Here is the model of the signature we obtain. So our modeling is give a periodic signal at the Galileo orbital period, and this signal is modeled by an envelope of which the size defines the event duration. And our modeling actually depends on a set of 4 parameters: the crossing time of the Earth center by the transient core, the incident angle, so the incoming direction of the dark object, and finally, the event duration. So we decoupled our model signal into 2 parts: the signal strength depending on the coupling constant and the local dark matter density, and also the signal pattern. Indeed, we constructed a large bank of signal templates by the combination of the event parameters, considering also the Galileo satellite orbital data at a given time. So the clock data series contain, of course, the noise, but also the hypothetical signal induced by dark matter clump. And to try to highlight this signal, we used a match filtering techniques between clock data and template waveform. We also used the signal to noise ratio as a test statistic. So for our data analysis, we constructed the Galileo clock network noise covariance matrix. From that matrix, we calculated for each template the signal to noise ratio. And finally, from a set of mocked data, we computed the detection threshold from the maximum SNR distribution. And there are two possibilities. First, if all the SNR templates are below the threshold, we can state there is no data in the data, no event in the data stream. But any templates of which the SNR is above the threshold can be considered as a candidate event. And the result is the following. For the template lasting between 1 day and 60 days, there is no candidate events found in the dataset. But for templates lasting between 16 days and 100 days, over 1 year of observation, up to 10% of event has a SNR which is above the threshold according to the observation epoch, and so can be considered as candidate event. And so here I presented the variation over 1 year of the direction in the celestial sphere of the signal with the highest SNR at a given time t. And so the conclusion is that the signal does not come from a fixed point in the celestial sphere, which is a quite bad news for dark matter model and dark matter origin. And so the hypothesis is that perhaps some systematic effects at orbital period has not well taken into account. First investigation, orbital mismodeling. We know that orbit mismodeling is strongly correlated to clock errors. And so we performed an intensive satellite laser ranging during 3 months in 2021. It was used to explore if mismodeling of, for example, solar pressure radiation could be responsible for the large SNR. And the answer is clear, no. The observed signal is 3 orders of magnitude larger than the estimated systematic uncertainty due to orbital mismodeling. Then we consider what seems to be the most obvious systematic effect. We studied the variation of the Earth's magnetic field along the orbit of the Galileo spacecraft. The magnetic field itself, but also the magnetic force and the Foucault current, because the satellite is in motion in the geomagnetic field. And finally, we study the variation of the satellite panel angle of illumination because we know that it is related to the temperature variation inside the satellite, which can affect the clock. And so the result is clear. There is no correlation between the modeled systematic effects and the seeked transient signal. In other words, if we consider the result with or without the systematic effect, it changes nothing. That means that we have discovered a genuine significant transient signal of a non-origin in the clock data with the following characteristics. At orbital period, it is modulated, it is transient. And so as a conclusion, we have candidate events, but after a finer analysis of systematic effect, it is impossible to exclude some model for transient variation of fundamental constant because we have discovered an unknown effect. Of course, what could be this origin of this effect? It is investigated. It could be due to an engineering problem affecting all the Galileo clock. But more interestingly, it could be an effect which has not taken into account, for example, related to space weather, like solar X-flare or solar wind. Thank you for your attention.